Hey Siri, what's the weather like? Alexa, play my favorite song. Have you ever stopped to wonder how these little devices understand everything we say? It feels like magic, but it's actually the incredible science of artificial intelligence. Today, we're diving deep into the fascinating world of automatic speech recognition to uncover exactly how AI deciphers our every word. Stick around, because by the end of this video, you'll see your voice assistant in a whole new light. So let's start at the very beginning. When you speak, you create sound waves. These waves are vibrations traveling through the air. The first thing your device does is capture these waves with a microphone. Inside the microphone, a tiny diaphragm vibrates in response to the sound, and this physical movement is converted into an electrical signal. This signal is an analog representation of your voice, a continuous wave of varying voltage. But computers don't speak analog, they speak digital. So the next step is to convert this analog signal into a digital one. This process is called sampling. The system takes thousands of snapshots of the analog wave every second and converts each snapshot into a number. This stream of numbers is the digital version of your voice. Think of it like turning a smooth, flowing river into a series of still photographs taken one after another. Now we have a digital signal, but it's not perfect. The world is a noisy place. Your voice signal is probably mixed with the hum of your air conditioner, traffic outside, or other people talking in the background. Before the AI can even begin to understand what you said, it needs to clean up this mess. This is where noise reduction algorithms come in. They are trained to identify and filter out these background noises, isolating the clean speech signal. It's like having a superpowered audio engineer meticulously removing all the unwanted sounds, leaving only the crystal clear recording of your voice. This clean signal is what the AI will actually work with. With our clean digital signal ready, the real AI magic begins. The system's first task is to break down the complex sound wave into its most fundamental components. In linguistics, these basic units of sound are called phonemes. For example, the word cat is made up of 3 phonemes: the K sound, the A sound, and the T sound. English has about 44 of these phonemes. The AI's job is to slice up the audio signal into tiny segments, typically just a few milliseconds long, and figure out which phoneme is being spoken in each segment. It's like listening to a word very slowly and identifying each individual sound that makes it up. This process of converting the audio signal into a sequence of phonemes is the first major step in decoding your speech. Now, how does the AI actually match a piece of audio to a specific phoneme? This is where the acoustic model comes into play. The acoustic model is a core component of the speech recognition system, and it's essentially a massive database that maps sounds to phonemes. It's been trained on thousands upon thousands of hours of speech from countless different people. This training allows it to learn the various ways a single phoneme can sound. After all, my A sound is different from your A sound, and it's just even different from my own A sound when I am happy versus when I am tired. Modern acoustic models often use powerful neural networks, like convolutional neural networks, or CNNs. You might have heard of CNNs being used for image recognition, and it's a similar idea here. They look at a spectrogram, a visual representation of the audio signal, and identify patterns. Just like a CNN can learn to spot the features of a cat's face in a photo, it can learn to spot the characteristic visual patterns of each phoneme in a spectrogram. By comparing the patterns in your speech to the vast library of patterns it has learned, the acoustic model calculates the probability of which phoneme is being spoken at any given moment. The output isn't a single answer, but a list of possibilities, like, I'm 80% sure this is a K sound, but there's a 15% chance it's a G sound, so now we have a sequence of probable phonemes. For example, the I might think it heard ka-t or maybe ka-p or even ga-t. How does it decide which one is correct? This is the job of the language model. The acoustic model understands sound, but the language model understands language grammar, syntax, and context. It knows that cat is a common English word, while cap is less common. It knows that a sentence like, the cat sat on the mat makes grammatical sense, while the gat sat on the mat is less likely. The language model uses another type of AI, often a recurrent neural network, RNN, or more recently, a transformer model. These models are experts at analyzing sequences. They look at the string of phonemes provided by the acoustic model and calculate the probability of different word combinations. The language model considers the context of the entire sentence. If you said, I need to feed the model knows that cat is a much more probable word to follow than, say, cap. It works hand in hand with the acoustic model. The final decision is a combination of what the acoustic model thinks it heard and what the language model thinks makes sense. It's a sophisticated process of weighing probabilities to arrive at the most likely sequence of words you actually uttered. This combination is what allows the system to distinguish between similar-sounding phrases like recognize speech and wreck a nice beach. The sounds are similar, but the context and language structure make one far more likely than the other. But how do these models get so smart in the first place? The answer is training, and lots of it. Both the acoustic and language models are built on neural networks, which learn from data. Imagine a student studying for a massive exam. That's essentially what these models do. Developers feed them colossal datasets. For the acoustic model, this means thousands of hours of labeled audio, where humans have already transcribed the speech. The model listens to the audio, makes a guess, and compares its guess to the correct transcription. If it's wrong, it adjusts its internal parameters to get closer to the right answer next time. This process is repeated millions of times. With each iteration, the model gets a little bit better at recognizing the subtle patterns in human speech. Similarly, the language model is trained on an enormous amount of textbooks, articles, websites, basically a huge chunk of the internet. By analyzing this text, it learns the rules of grammar, the relationships between words, and the common ways people structure sentences. It learns that is often followed by a noun, or that the word play is often followed by the name of a song or a game. This massive training process is what gives the models their incredible ability to understand language with such accuracy. The more diverse and extensive the training data, the more robust and accurate the AI becomes. Of course, speech recognition is not a solved problem. AI still faces some significant challenges. One of the biggest is accents and dialects. A model trained primarily on American English might struggle to understand someone with a thick Scottish or Australian accent. The pronunciation of phonemes can vary so much that the acoustic model gets confused. Another major hurdle is noise. We talked about noise reduction, but in extremely noisy environments, like a crowded restaurant or a windy street, it can be nearly impossible to isolate the speech signal cleanly. If the "I can't hear you clearly," it can't understand you. Homophones, words that sound the same, but have different meanings, like to, and to, also pose a challenge. Context is key here, but sometimes even context isn't enough, leading to funny or frustrating errors. And then there's the ambiguity of human language itself. Sarcasm, jokes, and idioms are incredibly difficult for an AI, which tends to interpret things literally. Despite these challenges, the future of speech recognition is incredibly bright. Researchers are constantly developing more advanced models. We're moving towards systems that can understand not just the words you say, but also the emotion and intent behind them by analyzing your tone, pitch, and speaking rate. Imagine a voice assistant that can tell when you're frustrated and responds with more patience, or one that can detect sadness in your voice and offer a word of comfort. We're also seeing the rise of end-to-end models that combine the acoustic and language models into a single, more efficient neural network. This simplifies the process and can often lead to even better accuracy. The ultimate goal is to achieve truly natural, seamless human-computer interaction, where talking to an AI feels as effortless as talking to another person. We're not quite there yet, but with the rapid pace of advancement in AI, that future might be closer than we think. From a simple sound wave to a complex understanding of language, the journey is a testament to the power of artificial intelligence. Thank you so much for watching. If you found this explanation helpful, be sure to hit that like button and subscribe for more deep dives into the world of tech and AI. Let me know in the comments what you'd like me to explain next. See you in the next video.